We are going to look at transformations, both rigid and non-rigid. So transformations affect the appearance of a parent function. There are two main types. Rigid transformations just change the position or orientation. So translations and reflections are rigid transformations. The basic shape stays the same, we just move it or flip it in some way. Non-rigid transformations, though, distort the shape of the function by changing its size. So dilations are non-rigid transformations when we stretch or compress a function. So you need to memorize these rules. Some of them hopefully you remember from Algebra 2. The first one we referred to as the k-value in Algebra 2, so we'll use that here as well. But remember, we could use any letter to represent this. We just need to understand that when a number is being subtracted outside of the function's main operation, it's going to shift the function downward. If we would have a number outside the main function operation being added, then it will shift the function upward. So down would correspond to this purple-looking graph here, and up would correspond to the green one. This is our parent function. So all we did was take this and slide it up if we had a number outside the main function operation being added, or slide it down if we had a number being subtracted. If we want to shift left or right, we refer to that as the h value in Algebra 2. And h is always inside the main function operation, and it's the opposite sign of what you see. So if you see x plus a number, then it means that h is actually negative and we've shifted to the left, so it would correspond to this graph here. If we would see x minus a number, then we know h is positive and it would have moved right. It would correspond to this green graph here. So again, here's your parent function, y equals x squared, our basic parabola. If we change it to be x plus 1 squared, then it would shift to the left. If we would change it to x minus 5 quantity squared, then it would shift to the right. The other one we talked about in Algebra 2 was the a value, so the number out front, and it controls two different things about the function, the direction it's facing and the stretch and compression of it. So what we learned was if we have a number in front of the function, we refer to that as the a value. And if the absolute value of a is less than 1, it's compressed. It slows it down from top to bottom and makes it a wider looking graph. If we have a number out front being multiplied by the main function operation and that number's absolute value is bigger than 1, it's going to stretch it upward and it appears skinnier like this purple graph here. We take the absolute value because we don't care about the sign, just the number itself. If it's less than 1, slows it down vertically, compresses it. If it's bigger than 1, once we get rid of the sign, then it stretches it vertically, pulls it up, makes it appear skinnier. So the function will compress or stretch vertically by a factor of a, whatever the number is sitting in front, being multiplied by it, regardless of sign. Because the only thing the sign tells us is whether it's positively oriented or negatively oriented. When we have a negative number, that's when it reflects vertically across the x-axis. So this is when you have an a value that's less than 0, and we know that our output is the opposite of what we had before, and it flips it vertically over the x-axis. So this is your vertical translation. This is the one we saw in Algebra 2. So if we make a negative, it takes it from this to this. It flips it over the x-axis, reflects it vertically. Now we're going to add on a new value here in Precalculus, and for this one, so we're going to refer to it as the b value, but again, we could use any letter to represent this. So if b is less than 0, it's going to reflect across the y-axis. So now the y values are going to equal f of the opposite of x, and this is your horizontal reflection. So instead of flipping top to bottom across the x-axis, now we're flipping right to left across the y-axis. The b value is going to be found inside the function operation, so it would be Now we'd have the function, and instead of being evaluated for just x, it's b times x. And it's going to stretch or compress the function by a factor of 1 over b. So we've got to take the reciprocal. A horizontal stretch is the opposite of what you would think with like an a value for the vertical stretch or compression. Whatever number we have there, we've got to take the reciprocal of it. So it's going to be compressed if b is greater than 1, because when we take the reciprocal of that, we'd have something less than 1. And it will stretch if b is greater than 1. Again, absolute value, so regardless of sign, the sign's just going to cause the reflection over the y-axis, right to left. So if we get rid of the sign, oops, I wrote this wrong, sorry. So if the absolute value of b is less than 1, then it actually means it's a stretch, because we got to take the reciprocal of it. So the b value is kind of like h. H, you've got to do the opposite sign. With b, you take the reciprocal of it. So if it's a value inside the main function operation, something about it is opposite of what you see or think. So let's take a look at some examples here. All right, so when we talk about locator point for each function, we're talking about the hk values, the left and right and up and down translation. So remember, h for horizontal, shifting left and right, k for up and down, like the sides of your k. And it is always supposed to be x minus the h value, so h is opposite of what you see. So in this first example, h is positive 3, k is always outside the main function operation, and it's exactly what you see. So your locator point for that parabola is 3, 2. That would be the coordinates of the vertex. Number 2 is a cubic polynomial. This value is inside the function operation, so that tells me it's the h value, and I got to make it the opposite sign. Since there's nothing out here, it tells me k is 0, so the locator point for this would be negative 4, 0. That would be the center of that stretched out S shape we get when we graph a cubic function. Number 3, h positive 6, k negative 8. So your locator point is 6, negative 8. And that's a square root function, so for that function, that would be your starting value. You wouldn't have anything prior to that. Number 4 is absolute value. H is positive 2, k is 9. So your locator point is 2, 9. That's a V-shaped graph. Anytime we graph absolute value, so that would be the vertex of that V shape. All right, cosine and sine. So we will be learning to graph these in this course, but we can still identify a locator point with the same steps we did before. So h is going to be inside with the x, opposite sign of what we see. K will always be outside, so our locator point here would be negative pi, comma 1. And this 4 out front would be an a value, so it would stretch this graph vertically. Number 6, so h value would be positive 3 pi over 4, and since there's nothing out here, k would be 0. So our locator point, which we will see later what that means for these graphs, would be 3 pi over 4, comma 0. This negative 2 here would be the a value, so the negative would have reflected vertically. So across the x-axis, it would also be stretched because of the 2. This 4 would be the b value, so we take the reciprocal of that, we get 1/4, so it's going to compress it in the left to right sense. All right, so in this next section, given each function, identify both the parent function and the transformations. So number 1, the parent function here is going to be the cube root of x. So h here is negative 1, k is positive 2. So we've got negative 1, positive 2 as our locator point. And we have an a value of negative 4, which means it's reflected vertically over the x-axis. It's also stretched because the absolute value of negative 4 is 4, which is bigger than 1. So it's also stretched vertically. All right, number 2, the parent function here is the absolute value of x. H is -5, k is -2. So we've got a locator point of -5, -2, which means we would have moved left 5, down 2. And this value, since it's inside, is the b value. So we take the reciprocal, and it would be compressed by 1/3 horizontally, left to right. Because remember, the b value, we have to take the reciprocal of it to determine your stretch and compression in a left to right sense. All right, number 3, we have a square root function. This is your h value, so it's +1. There's nothing outside, so k is 0. So your locator point is 1, 0, meaning that the graph has just moved right 1. It hasn't gone up or down at all. This negative is your b value. So because it's a negative, it would be reflected across the y-axis, so horizontally. And this one here is your a value, so it would be stretched vertically since 2 is bigger than 1. All right, so number 4, the parent function here is the reciprocal function, or the rational function. So there's nothing being subtracted from x, so h is 0, k is 3. So locator point is 0, 3. For these graphs, remember that's the intersection of the asymptotes. So it would have moved up 3. And then there's a couple of different ways that you could look at this. I'm going to say it's the a value. You could also think of it as the b value. So an a value of -1/4 means that it would be reflected vertically. And then compressed. It would look the same if you said it was the b value and we reflected across the y-axis horizontally. Talked about structural compression there. The graph would look the same, so you can interpret it both ways there. All right, number 5, we have the greatest integer function. So our locator point here is 5, -1, so it moved right 5 and down 1. And so this value inside, so b equals 1/2. So we think of the reciprocal of that as being 2. So this is stretched horizontally. Number 6, we've got a cubic function. So here our locator point is -3, -8. So left 3, down 8. And then a equals -3/2. So it's stretched vertically because 3/2 is bigger than 1. And it's reflected vertically over the x-axis because it's negative. So we want to get really good at that, looking at an equation, identifying, okay, what kind of function is this? What's the parent function? Get a basic sense of the shape of that graph in your head. Then identify the locator point to think about how it's moving. That central point is moving left, right, up, down, and then analyzing an a and or b value to see has it been reflected over either of the axes, has it stretched, is it compressed. All right, so using the graph of each function, identify the parent function, then write an equation for the function under each transformation. So when I look at this graph, I see that V shape. I instantly know it's the absolute value function. Oops. So to vertically stretch, that means we need an A value of 3. And 4 units to the right means that H is 4. So A value goes in front of the function operation. H value gets subtracted from X inside the function operation. So we need 3 times the absolute value of X minus 4. All right, if we're going to reflect across the x-axis, that's vertically. So we need an A value less than 0. We need a negative number out front. 5 units up means K is 5. So we will say f of x equals negative absolute value of x plus 5. All right, a couple more examples here. So number 8, as soon as we see that stretched out S shape going left to right like that, we know that is the cube root function. So the parent function is f of x equals cube root of x. To reflect across the y-axis, that's a left to right reflection, so that tells us the b value must be less than 0. And translate 3 units to the left tells us that h is negative 3. So both of these things need to be inside the function operation. So under this cube root symbol, I'll need a negative for the negative b, and then I need x plus 3 because it's x minus a negative 3, so it becomes x plus 3. Or we could choose to write that as the cube root of negative x minus 3, either way. All right, letter C, horizontally compressed by a factor of 1/2. Means that your b value is actually going to be 2, because remember it's the reciprocal of the stretch or compression, and then translate 5 units down means k is negative 5. So for our function, we would need the cube root of 2 times x, and then outside of that is the minus 5. All right, so we're going to find the equation for the reflection of f of x equals 5x minus 9 divided by x squared plus 3 across each axis. So across the x-axis is vertically, so that means the a value is 0. So we're going to take our function and we're going to multiply it by negative 1. Remember, when you take a number times a fraction, a whole number, it only affects the numerator. So we only distribute that negative to the top. The denominator would stay the same. So we would get negative 5x plus 9 over x squared minus 3. Then if we want to reflect over the y-axis, that means that our b value has to be less than 0. So we gotta replace the x's with negative x. So we're going to get negative 5x minus 9 over the x squared plus 3 for the horizontal left to right reflection across the y-axis. All right, number 10. Let C1 be a curve defined by f of x equals x cubed minus 16x. Find the equation for the following non-rigid transformations of C sub 1. So C sub 2 is a vertical stretch by a factor of 3. So a vertical stretch means the a value is 3 and it multiplies by the function. So we're going to get 3x cubed minus 48x. Letter B, if we want a horizontal shrink by a factor of 1/2, that means that the b value is 2. So instead of x, we got to replace all of those x's with 2x. So if we cube it, we'll get 8x cubed minus 32x for that equation. So remember, the a value goes out front and multiplies by the function. The b value goes in with the x, and it's always the reciprocal. And those are your transformations. Really practice and make sure you have a great understanding of them. It will make graphing and understanding your functions a lot easier.